Unit 5, Day 17 notes, and they start on page 46. And we're back to looking at, just for the last time here, implicit relations. So implicit relations are those relations that you can't easily solve for y. And so we leave them in implicit form where the x's and the y's are all kind of mixed together. A lot of times implicit relations are not functions. So they're things like sideways parabolas or circles or ellipses or hyperbolas or something like that. We can't take care of them in a traditional fashion. So the essential question for today is, how can we apply the derivatives tests to implicit relations? So just to kind of give us a big picture here, what we're going to do, we know that derivatives of implicit relations tell us the same thing as what derivatives tell us, right? Derivatives, I say derivative, you think slope. So derivatives is the slope of the tangent line to the relationship. And so what we're going to review today is, how do we find y prime implicitly and how do we find y double prime implicitly? We're going to review that the chain rule comes into effect here and is very important when differentiating, because we're differentiating y terms. We're going to revisit finding the derivative so that we can substitute in coordinate values to find the slope of the tangent line. All of those skills that we've kind of interjected in almost every unit, that skill of the tangent line. And we're going to apply connecting y prime with the terms in this unit. So we're going to connect y prime, the first derivative, with the terms increasing and decreasing. We're going to connect y prime with writing tangent lines. We're going to connect y double prime with concave up and concave down, so concavity. And we're going to connect y prime and y double prime with maximums and minimums. If looking at this in the lens of Unit 5, this first bullet item is like the first derivative test. This is concavity, and along with it comes points of inflection. And then this last one here is the second derivative test. So we're gonna apply those implicit relationships with that lens. So before we jump into looking at some problems, we want to revisit that, just a real general kind of idea here, that when we do implicit differentiation, we typically get a derivative that has a rational form. So here's this general idea of, this is what a rational form looks like, right? Rational form is a fraction. And so just in real general terms, any rational expression is going to behave this way. And that's going to help us determine tangent lines. So keep in mind that this y here could be y prime or y double prime. It's just something that represents this rational expression. And so we know that if the top is 0, that's what this first line is saying here, if the top is 0, f of x is 0, and g of x is not 0, then this whole expression is 0. If g of x is 0, if the denominator is 0, and the numerator is not 0, then we have a rational expression that does not exist. So 0 over any number, and we get 0, any number over 0, and we get infinite or do not exist values. And so these two scenarios are going to help us find horizontal. This top one's going to help us find horizontal tangent lines, and this bottom one's going to help us find vertical tangent lines. Because when we talk about this being the expression of the derivative, I say derivative, you think slope. So having the top 0 would be a slope of 0, and having the bottom 0 would be having a slope of infinity, which would be a vertical line. If they're both 0 at the same time, f of x and g of x, then we have a big problem, right? We have an indeterminate form. This is not going to occur in the context of these problems. So we're not going to really have to worry about it, but acknowledge that if that's the case, then we have an indeterminate scenario, and we just kind of don't talk about that in terms of the context of Unit 5. Okay, so let's take a look at this first problem here. So in this question, we say let C be the curve defined by x squared times y equals 4. So we could solve this for y and differentiate it traditionally, but we're going to differentiate this implicitly. It's a real common scenario that they give you, and so you should be comfortable differentiating this implicitly. Which of the following statement is true about curve C at the point 2, 1? Okay, so looking at these options here, we're talking about relative minimums, relative maximums, concavity. You know that we need to find the first and the second derivative and know what those values are. So let's differentiate this. So we have x squared times y equals 4. So we have a product rule we need to use here. Think of the x squared as u and the y as v, right? So we need u prime v plus uv prime. So differentiating x squared gets us 2x times y. So that's u prime v plus uv prime would be x squared, and then differentiating y as 1y prime. So I'm just going to write that as y prime. And then equals, and then differentiating 4 gets us 0. So we're solving for y prime here, which means we take the 2xy to the right side and divide by x squared. So we get y prime equals negative 2xy over x squared. Substituting in 2, 1, we get negative 2 times 1 over 2 squared. So this is top is negative 4, the bottom is 4, so that's negative 1. So we know the first derivative is negative. So just from finding the first derivative, we can narrow down our choices to either C or D. Because we don't have a first derivative that's equal to 0, we have a first derivative that's negative. So we know we don't have a min or a max at this location because we don't have a first derivative. Okay, so here is my first derivative. We need some information about the second derivative. So we're going to differentiate this expression, negative 2xy over x squared, using the quotient rule. And when we differentiate the numerator, we have negative 2x times y. So we're going to need the product rule up here. So we know that the quotient rule is low d high minus high d low over low squared. So we have low, which is x squared, times d high. So this is where we need the product rule. So I'm going to set up some brackets here. And so think of negative 2x as your u. Think of your y as your v. So we need u prime v plus uv prime. So u prime is negative 2 times v, which is y, plus, now it should be a plus, but I'm sticking a minus here for a reason, because we have a negative here. So plus u would be negative 2x. That makes sense. It changes the plus to a minus because it's a negative 2x for u. And then the derivative of y is 1y prime again, so I'm going to call that y prime. So in this bracket is the chain rule. Let's just review this one more time. We have u prime v plus u, that whole thing is u, negative 2x, times v prime. So we have low d high. That's just low d high. It's a lot going on there. It's just low d high minus high d low. So high d low is negative 2xy times the derivative of low is 2x. So that's low d high minus high d low all over low squared. So squaring this gives us x to the 4th. So there's our second derivative, which looks super messy. But really all we have to do, we need to know is whether it's positive or negative. So all we're going to do is substitute in 2, 1. So everywhere we see an x, we're going to put 2. So we're going to put 2 here, and here, and here, and here. And we're going to put n down here. And we're going to put 1 here, and here. And then where we have y prime, we're going to put negative 1, because we found that when we found the first derivative. So that looks like this. So we got 2 squared times negative 2 times 1, that's y, minus 4, because 2 times 2 is 4, times y prime, which is negative 1, minus negative 2 times 1 is all negative 4, times 2 times 2 is 4, all over 2 to the 4th. So doing this math here, we know that the bottom 2 to the 4th is 16. we have 4 times, let's see what we have here. We got -2 plus 4, so we get 4 times 2, positive 2, which is 8. And then this is positive, plus 16. So it looks like we have 24 on the top and 16 on the bottom. That's positive. That's all we really care about. So we know that y double prime is greater than 0. So that means it's definitely option C here, that we have a negative first derivative and a positive second derivative. So we're decreasing because of the negative first derivative, and we're concave up because of the positive second derivative. So your answer is C. There's a lot going on in this problem. This is definitely a take the full 2 minutes to do, might even take longer. So this is one of these problems that, you know, you invest maybe 3 minutes in, knowing that you're going to come across a question that's only going to take a minute. Okay, so let's take a look at this one. So this one definitely would be very cumbersome to solve for y and differentiate. Solving for y might not be too much of a problem, but differentiating what you got would be really messy. Okay, so it says that how many points on the curve, and this is the curve, x to the 2/3 plus y to the 2/3 equals 9. In the xy plane, does the curve have a tangent line that is horizontal? So a horizontal tangent line means the derivative is equal to 0. So we're going to use implicit differentiation to differentiate this. Okay, so we're going to start with differentiating x to the 2/3. So we bring down 2/3, x to the subtract 1, which would be -1/3. And then we're going to differentiate y to the 2/3, same fashion. It's going to be it's going to be 2/3 y to the -1/3, but then times y prime. Right? There's that chain rule because we're differentiating a y term with respect to x. And then we have to differentiate 9, which is 0. So there's our derivative. And we have to solve for y prime. So solving for y prime means bringing 2/3 x to the -1/3 over to the right-hand side, dividing by 2/3 y to the -1/3. So it's going to look like this. We've got some canceling we can do with the fractions 2/3, but don't forget we have a negative out front here. That stays. So we have this. So we need to know where this is equal to 0. So this is equal to 0 where the top is equal to 0. So all we really need to concern ourselves with, oh yeah, we need to take care of the -1/3. So really the y should be on top and the x should be on the bottom. We need to relocate these terms because they have negative powers. So all we need to concern ourselves, since we're just horizontal tangents, we just need to concern ourselves with when the numerator equals 0, because that's when the whole thing equals 0. So y to the 1/3 equals 0. When does that happen? Well, that happens if we cube each side. That happens when y is equal to 0. Okay. So the question is when is y equal to 0? And the answer is easier to answer when we know what value x's are when y is equal to 0. So when y is equal to 0, it's like we're looking at when it's crossing the x-axis. So we really need to know where on the x-axis we're crossing. So we're going to take y equal to 0 and we're going to substitute it into the original expression. So we're going to get x to the 2/3 plus 0 equals 9, and we're going to solve that. So we're going to, this x to the 2/3, we can solve that if we raise everything to the 3/2 power. So we're going to raise the left to the 3/2 and then right to the 3/2, and we're going to get that. And so that happens when x equals 9 to the 3/2 power. So let's think about what this means. This means that the half power means the square root of 9, and the 3 means cube it. So if we think about that in that terms, the square root of 9 is 3. And when we cube 3, we get 27. Okay. And the thing is, though, when we cube something, we could also cube a -27. We could take -27 to the 3/2 power, and also get a solution to this. Also get a scenario where y would be equal to 0. So we actually have two. This is what happens with odd powers, right? We can take positive solutions and negative solutions. So we actually have two solutions here where we have a horizontal tangent line. Let's take a look at another example. Example 3 here, which of the following describes the y coordinates? So we want to describe the y coordinates here of the points on the curve e to the x equals sine y in the xy plane, where the curve has a vertical tangent line. Okay, so now we're talking about where we have undefined slope or infinite slope. So we need to differentiate this. So so there's our infinite slope. So we know what that means in terms of a rational expression. That means we need to set the denominator equal to 0. So let's differentiate that so we can find our derivative. So we have e to the x equals sine y. Differentiating e to the x is e to the x. Okay, right? E to the x is its derivative of itself. Just a caveat here, it doesn't apply in this problem, but a lot of times we hide we hide a more complicated expression in the power, like x squared or 2x, and then we need a chain rule. So sometimes that might happen. It doesn't happen in this scenario though. Okay, now we need to differentiate sine of y. So it's a y term, so we know we're going to need a y prime. So we know we have a chain rule here. So the outside function is sine, inside function is y. So derivative of sine is cosine, so we have cosine y, and then times the derivative of y, which is 1y prime, or just y prime. Solving for y prime just means dividing by cosine. So we have y prime equals e to the x over cosine y. So now we want vertical tangent lines, which is where the denominator is equal to 0. So we're going to set cosine y equal to 0. So this rational expression doesn't exist when the bottom is equal to 0. So where's the cosine y equal to 0? Well, that happens when y is equal to a half, or when y is equal to 3/2 pi. Pi over 2 3/2 pi. So this is like the top of the unit circle and the bottom of the unit circle, right? That's when the cosine is 0. So knowing that, then we need to kind of look at our options here. So the real thing is all of these options apply to either like the pi over 2 plus n pi, like options A and C would catch pi over 2 and 3 of pi over 2. The pi over 2 plus 2n pi would catch pi over 2 and then skip over 3 pi over 2 and then go all the way around the unit circle. So the question is should we catch 3 pi over 2 or not? Is there some issue with 3 pi over 2 that we need to be aware of that would rule it out just based on these options? So let's substitute these values for y back into here. So when we do that, we get e to the x equals sine of pi over 2. Sine of pi over 2 is 1, and that has a real solution. That is x equal to 0, right? Because e to the 0 equals 1. So we know that pi over 2 gives us an x coordinate. So we have an x coordinate and a y coordinate that both exist. So we have a vertical tangent at 0 comma pi over 2. Let's take a look at this possibility for y. And so we put 3 pi over 2 into the expression for this expression. And we know that the sine of 3 pi over 2 is negative 1. It's at the bottom of the unit circle. And so that means e to the x equals negative 1. So if you remember back to our packet, our notes packet, we had the first page, we had all of those functions that I said it's really handy to know what those functions look like. One of them is e to the x. So we know that e to the x, it's impossible for e to the x to be a negative value. It's all up in quadrants 1 and 2. That's an exponential function. So this is impossible to happen. There is no x value that will give us this scenario. So that means we have no x coordinate to go with this y coordinate for a vertical tangent line to exist. So we have to rule out this and see that we only have viable solutions when we're at the top of that unit circle at pi over 2. And so we have then in this scenario where we do not want the 3 pi over 2. So and then to determine whether it's b or d, we know that we can have any integer for n. In other words, we can go forward through the unit circle or backwards through the unit circle. It doesn't matter if n is positive or negative. So we would choose d, the pi over 2 plus 2n pi for all integers n, both positive and negative. So that is that problem. So just a side note on questions 2 and 3, they're very tricky. The questions are definitely ones that require you to think and require you to really know those basic shapes of those functions. So keep that in mind. When we get back into the classroom, we'll review the takeaways for implicit differentiation in the context of Unit 5, and we'll work on some topic questions dealing with those topics.